Hi everyone. So in this video, we're going to be talking about a new topic that is related to limits. So we're going to be talking about continuity. So basically about what it means for a function to be continuous or discontinuous and how that's related to limits. So first definition, we're basically going to have two kind of different levels of definitions in this video. So the first definition of a function being continuous is going to be kind of like an intuitive definition, like the way that you would kind of explain it to someone. But then later in the video, we'll see that there's a more formal definition of what it means for a function to be continuous that actually uses limits. So this first definition says that a function is called continuous. It's basically what it sounds like. So a function is called continuous if it can be drawn without lifting your pen. So if it has kind of no breaks in the graph. So a function is called continuous if it can be drawn without lifting your pen. So basically, for a function to be continuous, it should not have any of the following. So a continuous function has no breaks, no holes, and no vertical asymptotes. So I'm just going to sketch a quick example of what a function might look like if it's continuous. So if you have a function that, kind of waves around, does different stuff, but it doesn't have any kind of breaks in the graph, no holes, no vertical asymptotes, then you would say that that function is continuous. So you would say that this function, f of x, is continuous on all real numbers. So in interval notation, you would say it's continuous on the interval from -infinity to infinity. Because as we'll see in a moment, there are functions that, parts of them are continuous and other parts aren't. So if you have a function that every single part of the graph is continuous, there are no holes anywhere, then you can say it's continuous on all real numbers. So next I want to look at an example of a function that has a bunch of different types of issues, basically. So this function here, let's maybe call this function g of x. So there are a few different places where this function is not continuous. So g of x is not continuous at x is equal to 1, right? So that's a place where we have a vertical asymptote. So just imagine if you were trying to draw this graph, you'd have to stop and pick up your pen, right, at x is equal to 1. So it's not continuous at x is equal to 1. It is not continuous at x is equal to 3, right, because in that place you would have to stop and lift your pen. It's not continuous at x is equal to 5 because there's a hole in the graph there. So again, you would have to stop and lift your pen, draw the hole, and then keep going. And then the last place that it is not continuous is at x is equal to 8. Similar reason, we have a hole. In that case, we have a point that's also drawn higher up, but either way, at x equals 5 and x equals 8, it is not continuous. So it is continuous at 6. I just want to point that out, that at 6, notice that the graph kind of has like a point to it. That's okay. That's still considered continuous. It doesn't need to be a smooth curve. It just needs to be kind of all one piece. So it can totally be jagged and still be continuous. So there's another way of kind of phrasing what we wrote up here. So I said g of x is not continuous. Another way of saying that is you could say g of x has discontinuities. So the word discontinuity just means basically a place where the graph is not continuous. So discontinuities at the same point. So I'll just write that down as well. And there's different names for these different types of discontinuities. I'm not going to really be like testing you on this, but just so you know, when you have a vertical asymptote, that is what's called an infinite discontinuity, because the graph is, you have this limit where the limit is going to infinity or negative infinity. When you have something like at x is equal to 3, that's what's called a jump discontinuity, because the two pieces of the graph are really like completely split apart from each other, right? So it's like a jump in the graph. And then both x is equal to 5 and x is equal to 8, those are both called removable discontinuities. And so a removable discontinuity is basically when you have a hole in the graph. And regardless of whether you have, so at 5, there's just a hole with nothing else. At 8, there's a hole, but then there's another point above. Either way, it's called a removable discontinuity. Okay, so I want to say a little bit more about, so far we've been looking at just graphs, and I just want to talk a little bit about different types of functions and kind of how you can figure out whether they're continuous or not, maybe without even looking at the graph. So in general, if you have one of those nice types of functions that we listed out in a previous video, so I'm going to list those again. So polynomials, rational functions. So again, polynomials are when you're adding up different powers of x. Rational functions are when you have a polynomial divided by a polynomial. Radical functions, so radical functions are square root or cube root or etc., different root kind of functions. Trig functions, sine, cosine, etc. Inverse trig functions. Exponential functions. Logarithmic functions. And then any kind of combination of these. And so that's something that we'll be seeing a lot in this class actually, is when we get further into the quarter, we're going to be dealing with lots of functions that are actually kind of mixes of these different types of functions that are listed out. So all combinations of these. So any function like the ones listed, these ones are going to be continuous at all x values in their domains. So it doesn't mean that they're continuous on all real numbers. It means that, whatever the domain is, the function is going to be continuous on that domain. So basically, in other words, so finding discontinuities, figuring out where the function is not continuous, is the same as finding where the function is undefined. So we'll see that this is not the case for piecewise functions. For piecewise functions, there's a little bit more work to do. But for these type of functions, if you're asked, where is this function continuous or where does it have a discontinuity, you're always going to be just looking at where is this function defined, where is it undefined. So for example, if we have the function f of x is equal to 5 times sine of 2x. So what is the domain of this function? Well, we know that the domain of sine of x is all real numbers, right? And so then what are these 5 and this 2, what are those doing? The 5 is a vertical stretch by 5. The 2 is a horizontal compression by 2. Neither of those is going to really change the domain, right? So the domain is still all real numbers. And so that tells us that this function is continuous on all real numbers, or I'll write it in interval notation. Because there's no, we're really just looking for, is there any number that makes this undefined? And then let's look at another example. So let's say that we had the function g of x is equal to x over x plus 1. So in this case, this function does not have a domain of all real numbers, right? There are numbers that would make this undefined. Specifically, what number would make this undefined? Well, we can't plug in -1, right? Because -1 would make the denominator 0. And so there's kind of two ways that you could talk about this. You could either say that this has a discontinuity at x is equal to -1, or you could say it's not continuous at x is equal to -1, or you could say it is continuous basically on every other x value. So if you remember interval notation from pre-calculus, basically we would want to write down all real numbers except for -1. And so that would look like -infinity up to -1 union -1 up to infinity. So when you're talking about discontinuities, you're just kind of saying the specific values where it's discontinuous. When you're talking about where is it continuous, you're kind of saying everywhere else. And so that will typically be, you're giving like an interval. It's continuous everywhere except for at -1. And if you were to look at the graph, you would see that this graph has a vertical asymptote at -1, but every other part of the graph is, fine. There's no holes, there's nothing else funny going on. So that's for these kind of nicely behaved functions. Just like with when we were talking about limits, things are a little bit different for piecewise functions. So if f of x is a piecewise function, it may be discontinuous at its transition points. And what I mean by transition points is basically the x values where it goes from one function to another. So I'm going to write down a couple of examples and we'll actually come back to these in a little bit. But if you have the functions f of x is equal to x plus 1, if x is less than 0, and then e to the x if x is greater than 0, or if you had the function g of x is equal to x if x is less than or equal to 0, and e to the x if x is greater than 0. So we'll actually look a little later in this video at actually figuring out what's going on with these two functions. But where would you need to check for discontinuities? Well, you would just need to check at 0, right? Because that's the place where, like, if you picture graphing this, you have two kind of pieces to the graph. And what you need to figure out basically is whether those two pieces match up. And if they match up, whether there's a hole in the graph or not, or maybe they don't even match up at all. And in any of those cases, if there's a hole or if the graph just doesn't match up, then it's not going to be continuous. So for these two, I'm just going to say that these could be, and we'll actually see that both of them are, but for now I'll just say could be discontinuous at x is equal to 0, because x is equal to 0, again, is basically this number, right? Is the place where we're switching from one equation to another. Okay, so I want to now talk about, as I mentioned, that kind of more formal definition of continuity. And then we'll come back to the first example we did and look at it with that like more precise definition. And then we'll also go back and do the examples that we just wrote down. So this is kind of the, like I said, the formal definition of continuity. So the formal definition of continuity says that a function f of x is continuous at x is equal to a if the limit as x approaches a of f of x is the same as f of a. So how should you think about this? Basically think about this limit part. So remember, the limit isn't talking about what's happening at x is equal to a. It's talking about where the graph is heading, right? It's talking about the general trend. So when you're taking the limit, you're looking at, where is f of x heading? Where f of x is heading when x is close to a. So it's like the trend. And then what is f of a? Well, f of a is the actual value. Of f of x at x is equal to a. So maybe another way of thinking about this is that the limit is what's happening close to a. So let me just kind of emphasize that part. So the limit has to do with close to a, and the actual value here is at x equals a. And so if you think about it, if the points close to a agree with the point at a, well, that kind of sounds like it should be continuous, right? Because that means that the graph is kind of heading right where it should. So I think this definition will probably become more clear when we look at some examples, which we'll do with this graph. So I'm going back to this graph from earlier, and so I want to focus on a few of these points. We're not going to do all of the points, but I want to look at x is equal to 3, x is equal to 8, and x is equal to, let's do 5 as well. So let's start with x is equal to 3. So we talked about earlier the fact that this graph is not continuous at x is equal to 3. So I guess we called this earlier g of x. So we already figured out earlier that g of x is not continuous at x is equal to 3. So I want to now kind of support that. We can tell just by looking at it that it's not continuous, but I want to show how this definition matches up with what we saw in the graph. So how do you kind of use that definition above? You basically want to figure out what is the limit, and then you also want to figure out what is the value when you plug in the function and see if those things agree. So remember that when you're dealing with a piecewise function, you have to find the left and the right-hand limit individually. You can't just say, oh, the limit is this. So the limit as x approaches 3 from the left of this function, that would be equal to 1/2, right? Because we're looking at what's the height that this graph is approaching as you come in from the left. And so the limit from the left is 1/2. And then if we're coming in this way, well, the limit from the right, so the limit as x approaches 3 from the right of g of x, that's going to be equal to 2. And so what does that tell us? That tells us that overall, the limit as x approaches 3 of g of x does not exist. And so as soon as the limit does not exist, it's going to be impossible for this definition up here to be satisfied, right? Because this definition says that the limit has to agree with the function. And that is only going to happen when the limit and the function are both numbers that agree with each other, right? So you can't have does not exist is equal to 3 or whatever. That doesn't make sense. So as soon as the limit doesn't exist, that already tells you that it's not continuous. But let's also talk about the actual function value here. So what would you get if you were to actually plug in 3? Well, g of 3, according to this graph, is 1/2. And so basically what we can conclude is that the limit as x approaches 3 of g of x is not equal to g of 3. And as we mentioned, that's basically because the limit doesn't exist. If the limit doesn't exist, there's no way it can possibly agree with the function. But we'll see that in the other examples we're going to look at, that's not always how it plays out. There's different ways that these can go, and yeah. So let's actually, sorry, I changed my mind. We're going to look at x is equal to 6, and then we'll look at x equals 8. I'm going to skip x equals 5 because we're going to do an example similar to that in a little bit. So let's say that we were now looking at x is equal to 6. So this function is continuous at x equals 6, right? So g of x is continuous at x equals 6. So how can we support this using the limit definition? We want to start by finding the left and right hand limits. And then see if those agree or not. And then we'll see if they do agree, whether that limit agrees with the actual function value. So the limit as we approach 6 from the left looks like it's -1, right? Because the function is heading towards a height of -1. And then same thing from the right. If we come in from the right, our graph is also getting closer to a height of -1. And so that tells us that overall, the limit as x approaches 6 of g of x is equal to -1. And then if we actually plug in 6 into our function, so if we plug 6 into our function, we see that the value of g of 6 is also equal to -1. And so that tells us that the limit as x approaches 6 of g of x is the same as g of 6. And so that tells us that it is continuous. So just to be clear here, because you might be like, well, didn't we already know it was continuous? Why were you doing all this? Basically, I want you to be able to tell by looking at a graph whether something's continuous or not. But I do want you to also understand this limit definition. And so in order to be able to understand this limit definition, to me, that says that you should be able to kind of write down all of this information and see in what way the continuity definition does or does not work in a given, at a given point. So let's do one more. So we know from earlier, we talked about how g of x is discontinuous. Sorry, I said earlier, I said not continuous. I'll just say that to be consistent. So g of x is not continuous at x is equal to 8. So how can we establish that? Well, let's take the left and the right-hand limit and see what we get. So we're taking the limit as x approaches 8 from the left, the limit as x approaches 8 from the right, so let's see what we get in each of these cases. So if we're coming in from the left, we see that we're getting closer and closer to a height of 1. So the limit as x approaches 8 from the left is equal to 1. If we come in from the right, the graph is still approaching a height of 1. So the left and the right-hand limits agree. And so we can then conclude that the limit as x approaches 8 overall is also equal to 1. And so now to determine whether it's continuous, we need to now compare that to g of 8. So what is g of 8? Well, if we look at the graph, we can see that there's a hole. So g of 8 is not equal to 1, it's actually equal to 4. That's the point that actually lies on the graph at an x value of 8. So g of 8 is equal to 4. And so in this case, now we can see that, if we compare it with the blue one, the limit didn't exist. So it was like not even possible for the limit to agree with the function. This one, the limit does exist, but it still doesn't agree with the function. And so we can then say that the limit as x approaches 8 of g of x is not equal to g of 8. And that supports the fact that we said it's not continuous. Okay, so the last thing I want to do is go back to those two examples that we talked about earlier, or that we mentioned earlier, and basically figure out whether these functions are continuous or not, and then also go back to that more formal definition and see how we can support our answer using that definition. So the first function I want to look at is f of x is equal to, so it's going to be x plus 1 if x is less than 0, and e to the x if x is greater than 0. So let's start by sketching this graph. And we'll see that you could probably do this without drawing the graph, but I just always like to draw the graph. I think, having the graph on hand, it's a lot easier to make sense of what you're doing, and you're less likely to make a mistake. So what is this graph going to look like? Well, the first part of it is x plus 1. So I'm just going to start by graphing that line, and then I'll erase the part of it that we don't want. So we're only supposed to use this part if x is less than 0. So that means we want to get rid of this positive part. And then we want to put an open circle on this point because it doesn't say less than or equal to, it just says less than. And then the next part of the graph is e to the x. So that would look like this, right? E to the x kind of comes down like this. It has a y-intercept of 1. And then it goes up from there. So it should be going through about like 2.7 when x is equal to 1, and it goes up like this. And so we want to get rid of this negative part, or the part, where x is less than 0. And so this is our graph. And notice that in this case, this one also says just greater than, there's no equal sign. And so we want an open circle on both of them. So we can see by looking at this graph that f of x is not continuous, or it's discontinuous, or it has a discontinuity at x is equal to 0. And so how could we use that limit definition to support that? Well, we could say if we take the limit as x approaches 0 from the left of f of x, and the limit as x approaches 0 from the right of f of x, in this case, those limits are actually both 1, right? Because when you're coming in from the left or coming in from the right, either way, you're heading towards this point 1. And another way you could do that is if you actually just plugged in 0 into the top and the bottom equation. In both cases, you would get 1. Even though you're not really supposed to plug 0 into either of them, right? Because you don't have an equal sign. If you're not saying that f of 0 is 1, you're just kind of plugging the number in to see where there would be a point if there was. So from here, we can conclude that the limit as x approaches 0 of f of x is equal to 1. However, f of 0 is undefined, right? There is no point at x is equal to 0. And so if f of 0 is undefined, there's no way that it could possibly be true that the limit as x approaches 0 of f of x is equal to f of 0, right? Same as if the limit's undefined, then they can't be equal. Same thing if the function's undefined. All right, last example. So let's do this one. So this one is g of x is equal to x if x is less than or equal to 0, and e to the x if x is greater than 0. So this function is supposed to look like a line, so a line through the origin. So again, I'm just going to draw the whole thing, and then I'll erase what we don't want. And so we're supposed to use this only if x is less than or equal to 0. So we can leave that negative part, get rid of this, and then I'm going to put a closed circle in this case because we actually do have this equal sign. And then the next part of the graph, we already saw this one, that's e to the x. And so e to the x would, if we had the whole thing, it would look something like this, which I forgot to do it in 2 pieces. So let me do that again. So like that. And then it would go from here up like this. But we don't want this negative part. We only want the positive part. And we also want to put an open circle because we have just a greater than, not a greater than or equal to sign. And so in this case, the limit as x approaches 0 from the left of this function is still equal to, or is equal to 0, right? Because the function is heading towards 0. But if we take the limit as x approaches 0 of this function from the right, then we see that we're heading towards a height of 1. And so together, those two things tell us that overall the limit does not exist. So we already know it's not going to be continuous, but let's also figure out, what is g of 0. So g of 0, you would use the bottom part of the graph. You would use the first equation. So g of 0 is 0. But even though g of 0 is defined, we still have to conclude that the limit as x approaches 0 of g of x is not the same as g of 0. So that's it for this video. So yeah, basically, main thing I just want you to understand from this is kind of two things: how to be able to tell by looking at something whether it's continuous or not. But then I do also want you to be able to connect what you're seeing visually in the graph with that limit definition. All right, I will see you all in the next video.